Hi, welcome. This is complex analysis, path integral 4. Hopefully, this will be a shorter session. I want to prove what I call fundamental theorem for path integral. Okay. What does fundamental theorem say? If if the integrand is a derivative of something, then computing the integral is easy. This is the basic idea, right? If I have to integrate a to b of dash, then it's easy. Then it is f of b minus f of a. That's what the basic 12th standard integration said. Integration is anti-differentiation, right? And similarly, if you come down to path integrals in vector analysis or two variable calculus, you must already learn something. If I have a force capital F, f of xy equal to u of xy comma v of xy, then I can define the path integral f over gamma. That is integral a to b f of gamma t dot product with gamma dot t. That's also derivative dt. That is the physical interpretation. It is the work done by the force when I move the particle along the path gamma from time a to time b. Again, one knows that it is dependent on the path, right? We on in our path integrals in the complex analysis we have seen, okay, the endpoints may be the same, but what we have seen is it depends upon the path. Path integral depends on the path, okay. But suppose my function f actually comes from as a derivative of something, restriction of a derivative of a holomorphic function. Can I say something more? This is what we want to say. Let us get started. So recall vector analysis or analysis of two variables, right? Suppose f is a force field on an open set in R2 to R2, so that f of xy is u of xy b of xy, right? Then suppose gamma is a path, let us say from a b to u, right? Then we define what is meant by path line integral. There in vector analysis one usually calls it line integral, what we call as a path integral over gamma. This by definition is f of gamma t dot product with gamma dash t dt from a to b, right? What we know is this integral f over f, capital F over gamma, depends on the path gamma. But if there exists a C1 function f from u to r such that f of xy equal to del f by del x, del f by del y at the point xy, that is the gradient of f at the point xy, then we know that integral of f over gamma is f of gamma b minus f of gamma a, and hence this such a field is called conservative field. If you want to learn complex analysis, you may think these are all not needed, but as if you had been a regular follower of my videos, you know that I always insist mathematics is a single unit. All subjects are interrelated. We should compare and contrast so that it enhances both the subjects, right? So in case you must understanding something about several variable calculus, this will also help you to understand with the proper perspective. Okay. Therefore, for conservative vector field, okay, therefore if I have two paths, this is one path gamma 1, this is another path gamma 2, this is the point from P to Q, this is sigma, right? Integral of f over gamma is the same as integral of f over sigma, because my f is gradient of f. It's a conservative vector field because it depends only on the endpoint. Therefore, it is little f of at q minus little f of at p. That's it, independent of path. Okay, this is what we want to look at. So, what should be our theorem? The fundamental theorem of path integrals. So, as usual, let f be a continuous function. Continuous. Gamma is a path from AB to U. Alright. Assume, notice that I have to know f only its values on the trace of gamma. Outside gamma, inside u, I may not even know whether f is defined. The function is defined. Understand that. That's very careful. Assume that there exists a g from u2 gu to c, which is holomorphic, so that when I restrict, this is my u and this is my gamma. When I restrict, this is my g, this is another c. When I restrict it to the gamma, then what do I want? G at gamma t is f at gamma t. This is for all t in AB. Okay, then what is that I want to claim? Then integral of f over gamma is g at gamma b minus g at gamma a. Therefore, if I have another path, okay, suppose I have another path, sigma, okay, this is sigma, let us make it, this is gamma. Suppose the points are A and B, right? And sigma may have some other domain. Sigma may be from CD to U, but the starting point, end points are the same, A and B. Then what do I want to say? Integral of f over sigma will also be equal to integral of f over gamma, because both the values both are nothing other than g of gamma b minus g of gamma a, which is same as g of sigma b minus sigma g of sigma a. Yeah, okay. The proof is extremely easy, right? Let's look at integral of f over gamma. This is by definition a to be f of gamma t gamma prime t dt. But what is f of gamma t? Sorry, g prime of gamma t is f of t, right? This is the derivative is what is important. Please go back, I made a mistake in the statement. Earlier I said it correctly when I wrote there is a holomorphic function, so that f is the derivative of the holomorphic function, right? Fundamental theorem always deals with integral of a thing when the integrand is a derivative. Keep that in mind. Okay, therefore this is g prime of gamma t gamma prime t dt, right? Now let's look at the function phi of t, which is equal to g composite gamma t, right? Now gamma, assuming that it's a piecewise smooth, etc., on this subinterval ti, I am using the standard notation, so I don't want to keep repeating. So on this interval, gamma is smooth and g is smooth on the entire u, right? Therefore this is smooth on this function as t going to, therefore t going to phi of t is smooth on ti minus 1 to ti, right? Therefore I will break the interval here to be as summation ti minus 1 to ti, I is running from whatever it is 1 to n or whatever. You follow that? So we will assume our gamma is smooth. Therefore let's assume gamma is c1 on AB itself, so that life is easier for us, right? Otherwise I have to break the integral into summation. So this is nothing other than So let's look at the function t going to g composite gamma of t. Therefore, by chain rule, g composite gamma prime t is what? G prime at gamma t into gamma prime t, right? Therefore, this fellow is nothing other than a to b g composite gamma prime t dt, right? But this, now we use the fundamental theorem of calculus for functions, okay, from an interval to c. Therefore, this is nothing other than g composite gamma at to b minus g composite gamma at a, right? So the result is proved. Pause, review, proceed. Okay, so this is something fantastic we are going to use. Therefore, as I said, suppose I have 2 points P and Q in U, and there are two paths gamma and sigma, such that the initial endpoints are the same P and Q, right? Now my my f, which is a continuous function, okay. Now what kind of continuous function it has to be? It has to be defined on over f as well as over g, the trace of f and g. Okay, so let us explain that. I didn't explain that properly there. Let me do that. So suppose f is from u to c itself is continuous, right? And let's assume there is a g from u to c holomorphic such that g dash equal to f on u, right? Then fix P and Q, 2 points in U, let gamma and sigma be paths. Okay, gamma may be from A to B to U, and sigma may be from C to D to U, but gamma at A equal to sigma at C equal to P, and gamma at B equal to sigma at D equal to Q. You see that now I am assuming, because what do I want? So this is, as I said earlier, this is one path gamma, okay, this is a second path sigma, and these are the points P and Q, right? Now my entire f is defined on all of u. This is my u, right? My f and g's are functions from here, right? F, g are functions. This is my f, this is my g, this is function to c. They are continuous. Therefore, in particular f and g, when I restrict it to the trace of gamma or trace of sigma, it is continuous. Do you follow that? Right. Now what I want to talk about is the theorem clear now? Then what do I want to say? Integral of f over gamma is integral of f over sigma. Why? Because this is both is equal to, by assumption, what did you know? Where is my cursor? Yeah, this is this fellow is equal to g of gamma a minus g of gamma b minus g of gamma a, and right, and this fellow is g of sigma d minus g of sigma c. But this is g at q minus g at p. This is also g at q minus g at p, right? So this is a corollary. What is a corollary? Corollary is the following. Okay, what is the corollary? Let f and g be continuous functions. Sorry, f be a continuous function. Sorry, this is not g. That is, f is continuous. This is g is holomorphic. This is continuous. Okay. Now f is a continuous function from u to c such that there is a holomorphic function g from u to c such that the derivative of g dash equal to f on u. Now suppose fix 2 points p and q in u. Let gamma and sigma be two paths which connecting p and q. Okay, when I say paths, their domains of interval domains may be different also, but the initial and end points are the same, p and q, right? Now therefore I can, since f is continuous on all of u, f is continuous on the trace of gamma as well as trace of sigma. Therefore path interval f over gamma, path interval f over sigma are defined. Okay, but I claim they are the same. Look at that, they look on different sets which you seem to be doing, but the final result is the same because of the fundamental theorem of path integral. Okay, please pause, review, proceed. So yet another corollary which will be very useful is, suppose gamma is a path which is closed, that is the initial point of gamma equal to end point, then we say gamma is closed path, right? Then what do you expect here? And again f equal to some g dash, f is a continuous function from u to c, if you want only over gamma for this matter, and g is a continuous function. Okay, let us assume f is continuous function. Okay, f is a continuous function u to c, because where we want to apply f will be actually a continuous function on all of u, and g is a holomorphic function from u to c such that g dash equal to f. Then integral of f over gamma is 0. This is clear. Why? Because this is equal to g of gamma b minus g of gamma a, but both are the same point. Let us call it p. So this is g of p minus g of p, therefore 0, right? Now, so we have proved fundamental theorem of for path integral. We had also seen two immediate corollaries. Yeah, I do not know where I stopped. Okay, yeah, so let us assume this is where. So let f be a continuous function from u to c. Assume there is a g such that g from u to c is holomorphic such that g dash equal to f, right? Let us take two paths, gamma and sigma, paths in u, but their endpoints are the same. That is gamma at a equal to sigma at c equal to p, gamma at b, the endpoint, terminal point of gamma equal to terminal point of sigma, which is sigma d, which is equal to q. Then I want to say integral of f over gamma is same as integral f over sigma, because both are equal to g at sigma d, which is g at q, and minus g at sigma c, which is g at p. Similarly, integral over f will be g at gamma b minus g at gamma a, which is g of q minus g of p. Therefore they are the same, right? That's the first thing, please go through it. And the second thing is, suppose I have a path gamma which is closed path. What does that mean? The initial point equal to end point, that is gamma b is same as gamma a, right? So let us start with the function f which is continuous from u to c, and g is a holomorphic function u to c such that g dash equal to f. Then integral of f over the closed path is 0. That is very clear, because integral of f over that will be g at the terminal point minus g at the initial point, but initial point is same as terminal point, g is a function, therefore the value is 0. Is that clear? So these are the applications. PRP. I forgot to share. I hope now I share this. It should be clear. Now let's look at, okay, revisit some example. Right. Let's look at z minus a to the power n when n is a natural number or n is z plus, right? Then this has a primitive. This is defined where this called this f. This is defined on all of you. You equal to c to c, right? Okay. Now let's take a path gamma, which is equal to a plus r e power I t 0 less than or equal to t less than or equal to 2 pi, right? Okay, this is a path. I want to know what is it. We had already computed this, right? But let us look at this. Now z minus a to the power n. Okay, if I define g of z equal to z minus a to the power n plus 1 by n plus 1, then g dash equal to f on c, right? Now what is gamma? Gamma is a closed path. Therefore, what do I know about integral of f? This is 0. So this is already seen by a computation from the definition using the definition of path integral. Okay, please go through it. Okay, this kind of thing you should revise twice or thrice so that you feel confident you can do it any time. You should not simply accept it on faith. Yes, I have seen it, I went through the proof. That's not enough. You can give the proof now. That is very important because they are all very easy, right? Okay, now I want to give a very interesting example. With that I will stop this session. Do you remember we did that dz by z minus a, okay, and let us say gamma, where gamma t is a plus r e power I t 0 less than or equal to t less than or equal to 2 pi. This is 2 pi I, right? Okay, we had already seen it. Now what I want is I want to derive this, rederive this using gamma equal to, do you remember, gamma 1 star gamma 2 path integral along gamma equal to path integral along gamma 1 plus path integral along gamma 2, and fundamental theorem of calculus. I want to use these things. Okay, and we will also use on the way multivalued maps, which is a bugbear of complex analysis. Okay, lot of things which you learn. This particular example I want to use it. Unfortunately, I have not included in my book. If at all there is a second edition, I would like to include this example just so that you become comfortable. I am writing books not to give a very streamlined, very kind of terse book. I am writing a book so that you feel confident. Okay, so I give a lot of small simple examples so that you feel confident. Now let's look at this. Okay, let us start for the simplicity. Let me assume a is 0. Okay, a equal to 0. Therefore I have this path, right? Now this path gamma I can write it as union of two things, that is gamma 1, which is actually gamma restricted to 0 to pi, and equal to gamma 2, which is restricted to pi to pi. The map is gamma t equal to e power I t. Here also at gamma 2t equal to e power I t. Now if you notice, you will see that gamma 1 star to gamma 2 is nothing other than gamma, using our definition. Our definition of the juxtaposition of two paths. This is a very trivial exercise because what is gamma? So for second part, okay, remember what is this first one? b1 plus b2 minus a2. b1 is pi plus what is b2 minus, this is b2, this is minus a2, this pi, again 2 pi. Therefore domain of gamma must be a1 to b1 plus b2 minus a2, which happens to be 0 to pi, right? And similarly for gamma 2 is e power I t. So you can see it's exactly the same. Please convince yourself. Do not accept what I am saying. So stop. Okay, convince. Gamma is nothing other than gamma 1 star, gamma 2. Gamma as above is as per definition. Okay, make sure of this. Therefore let me write f of z equal to 1 by z minus a. Therefore integral of f over gamma according to us is the integral of f over gamma 1 plus integral of f over gamma 2, right? Now let's look at gamma 1. What is gamma 1? 0 to pi, therefore it is this. This is my gamma 1, right? Oh, sorry, 0 to pi, sir. I'm very sorry. Okay. Right? So here I can take my thing to be, so whatever, see, look at this. Now since a is 0, remember I took a to be 0, therefore it will be easier for me 1 by z. Okay, now do I have a function g such that g dash equal to f? Intuitively we know that g must be log, but log we know is not completely defined on entire C star, but luckily this is one half plane, therefore if I omit one line I can define, right? For example, I can define 0 to pi, so anything will be 0 to pi. Do you understand this? Yeah, therefore I can define 0 to pi. Are you following? Yes or no? I am just omitting this, therefore if I want I can say minus pi by 2 to this 3 pi by 2. My alpha is minus pi by 2, right? Therefore log alpha is defined. Remember, whatever be the logarithm, its derivative is 1 by z, right? Because any two log alpha and log beta, they differ by a multiple of 2 pi. We know that 2 pi I if you want, right? Therefore it does not matter to us. Remember all these things. Don't get confused, because these things are never done. If you have not learned thoroughly, you will have problem. Go through it. And just testing you so that you really understand better. So this is log. Therefore here what do I have to do? Therefore this is log, therefore I have to look at log of this point, sorry, this is point 1 and this point minus 1. Okay, so therefore what is log of 1? Log of 1 will be 0 plus e power I theta, therefore it is going to be 0, I 0. And the other one is log of minus 1, that is log of 1 which is again 0, but then it is I times pi. Remember what is log? Log of any alpha z should be natural logarithm of mod z plus I times, okay, the theta alpha of z, where this fellow takes values in alpha to alpha plus 2 pi, right? Therefore this is 2 pi. You understand? Therefore 1 by z over gamma 1 is going to be logarithm with respect to whatever is minus pi by 2 branch evaluated between the what are the points 0 to pi. Okay, right? 0 to pi meaning, sorry, this is gamma 1 of 0, gamma 1 of pi, that is logarithm minus pi by 2 of gamma 1 of 0 is gamma 1 of pi is minus 1, therefore log of minus 1 minus log of 1, and this is pi minus 0, that is I pi. Pause, review, proceed. One way to say that you learn complex analysis from my course will be to learn this kind of examples, because usually these things are not done very carefully. Okay, I may make some small mistakes also, but don't bother, but you understand. Okay, now what are we using? On the half circle which lies in a slit plane on which logarithm is defined, which takes values from minus pi by 2 to 3 pi by 2. Therefore, there is a primitive for my function 1 by z. Therefore, I can compute. Right? Are you following? So we used logarithm, how to choose a proper logarithm as a primitive, and we use fundamental theorem of calculus, and of course we are also going to use path integral or addition of paths equal to addition of path integrals. Right? Okay. And now let's look at the last one, the second one. The second one is this one. So here -1 to +1, which goes, right? Therefore I can omit this fellow. Okay, therefore the angle will be pi by 2. My alpha equal to pi by 2. Therefore it's pi by 2 plus 2 pi will be pi by 2 if you want. Right? Pi by 2 to pi by 2. Sorry, if I may make a mistake, let me just use 2 plus pi by 2. Therefore 2 plus 2, 4 by, yeah, that's correct, 2.5. Yeah. Right? Okay, now let's look at here. Therefore this is the one which is slit. Okay, this is my r alpha. Therefore my u alpha, which is c minus r alpha, and which I have log alpha. Therefore what is log alpha of -1? So it has to take values from pi by 2. Therefore it is obvious choice is pi. And what is log alpha 1 now? It has to take values from pi by 2 to 2 pi by 2. Therefore 2 pi. Remember, what is the logarithm of 1? What are the all possible logarithm of 1? That will be 0 plus 2k pi, where k is natural. Therefore a 0, therefore I have to choose a case so that this lies here within this interval. Therefore it has to be this only. Do you understand this? There is no hanky panky. Therefore integral of f over gamma 2 is log 1 minus log of -1 alpha. Okay, that is 2 pi. There is sorry, I forgot I. Logarithm inverse I, remember? I pi, I 2 pi. I times 2 pi minus pi. Yeah, remember logarithm of z is ln of mod z plus I times theta of z, theta alpha of z. Okay, right. Therefore what do I get? This is again pi I. Right? Therefore integral of f over gamma, according to our result, must be integral of f over gamma 1 plus integral of f over gamma 2. Is this true? This we saw, this pi I, this is also pi I, therefore it's 2 pi I, and this we already computed, direct computation, we know it is 2 pi I. So the result tallies. Right? Go back. For many of you, the last example may be very demanding, because what are the things we are using? We are using the definition of path integral. We are using the definition of path integral or the juxtaposition of path equal to sum of the path integrals, and fundamental theorem of calculus, and choosing a correct branch of logarithm so that we can compute. Yeah, isn't it beautiful? Go through it. Okay, we will meet again.